general relativity, step by step. I made the peculiar observation that one crosses the horizon in a finite amount of proper, should have said proper, time. Even though, when we look at the Schwarzschild diagram here, it seems to indicate, well, it does indicate, that it takes an infinite amount of Schwarzschild time for even a light ray to cross the event horizon, which I've drawn in this kind of pink colour here. I've also got this diagram here which shows this nice case of, it shows geodesics, which are world lines of objects in free fall. So what we can see is that these objects fall, they're always within the light cone there, they're falling slower, but objects falling in, again, take an infinite amount of Schwarzschild time to cross that Schwarzschild radius 1. Their behaviour on the inside is even more peculiar. They actually go backwards or come downwards here because the local time coordinate is inward facing. And so they're always constrained to be within the light cones, but they're going downwards and to the left rather than upwards to the left here. Okay, so let's just go back to the algebra, which is here, I think. What I'm going to do is consider k. What I've been doing is consider k equals 1. What I'm going to do is to generalize that very slightly to a general value of k. You'll remember we've got this restriction on k that it's got to be greater than 1 minus, or the square of it has to be greater than 1 minus 1 over r. But we've still got a little bit of freedom to deal with k, so I'll show you how that works now. This is an absolutely typical part of general relativity. The concept is quite easy. This is just a straightforward differential equation, or a straightforward integral to do. It's just difficult, and I'll show you why now. No, I didn't mean that one, I meant this one. There we go. I've set up k as a variable here. Now what I want to do is to integrate 1 over the square root of k squared minus 1 over r with respect to r. Is that right? We've opened 1, 2, 3 with the square root, and I should close there as well. Okay, now it doesn't like it. It says, is k squared minus 1 positive or negative? It's basically saying that it's basically not sure if we're on an inward trajectory or an outward trajectory. That's the first uncertainty because it's the sign of the square root. But also it doesn't know that this is physically realistic. We've assumed here, or we've required, that k squared for physically realistic flow, physically realistic motion, we've got this restriction here, and it doesn't know, Sage doesn't know whether that restriction's in force. So I'm just going to have to tell it, if I can find it, here it is. So what I need to do is to tell it directly, assume that k is greater than 1. Let's try that. Will that work? It works, but as you can see, it's an absolute dog's breakfast. Absolute typical relativity, this. The concepts are easy, but the algebra is quite hard. I can try and simplify it. It might simplify a little bit. Simplify. Bonk. Doesn't simplify very much, does it? You see, it's an absolute pain in the neck, but it is fundamentally just algebra. Okay, so that's that. I'll minimize that. So we can solve this equation here for proper time and radial Schwarzschild coordinate. It's algebraically complicated but conceptually straightforward. And I'm going to stop there. Stop.